Nico. And if you say okay,
Okay.
yes, then perhaps you can start with a slow introduction or something, and then some further people will also arrive. Okay, please read. We are listening to your talk.
Thank you. Hello, everyone. It's good meeting with you, and well, I can't really say seeing you because I can't see most of you, but at least sort of being with you in this online session. My name is Piskovsky. I'm based at the University of Oxford, working with Philip Maini, whose picture you can see here, and who is my collaborator on this project and my supervisor, and also with Kevin Foster in the Department of Pathology, where I'm interested in microbes, their ecology, how they interact, and how all of this sort of arises from microbial metabolism. So maybe also something about chemical reactions, but that sort of work I will not talk about today. Today it will be more theoretical, more mathematical, and I'll talk about spatiotemporal patterns, specifically Turing patterns, and how they form in systems with many interacting species. So let's start with a question and with a problem. So this is the setup. We have a bunch of chemical species, and we put them together into some vessel, and then we go and try to mix them together. We have a well-mixed system, and we imagine that the system possibly goes to a stable steady state. And then we wait some time and stop stirring and see what happens. Well, there is a chance that actually nothing happens and that we are left with the state we started with. Or if we are lucky, we might see some sort of nice spatial patterns that are stable in time. Or if we are very lucky, we could even see possibly some sort of spontaneously formed dynamic patterns. And in this talk, I will try to address whether we can mathematically find conditions for when each of these categories, when each of these types of patterns appears. So let's try to formulate this problem mathematically. We have a system of ordinary differential equations for the abundances of these chemical species in the well-mixed system. And we assume that this system approaches a stable steady state. And then we look at the simplest possible transport of the molecules around, which is in our case diffusion. And we ask a simple question, can this diffusion give rise to these types of patterns? And if so, how? So how do we go about analyzing this? We start with the steady state, in this case called n star, and we make a small perturbation. In my case, I took a perturbation and I also go into the Fourier mode and I expand the perturbation in Fourier space, and then I study the growth rate of this perturbation around this uniform homogeneous steady state that is in this case lambda. And if you go and substitute that into our system, linearize, you derive just an eigenvalue problem where now the growth rate of this perturbation is just an eigenvalue of the matrix on the right-hand side, where we have the Jacobian matrix of the well-mixed system, which by assumption is stable, and so this matrix J has eigenvalues with negative real parts. And then we have the diffusion playing a role as this sort of second term, where we are subtracting a diagonal matrix with diffusion multiplied by wave number k. Well, in this, you transform to Fourier modes. What you have here playing a role, instead of spatial x, you go into the space of wave numbers. So k is a wave number. And so let's try to think about this problem in a very specific case. We start with a simple case where we have a single variable. Just imagine maybe an ink in the water. Yeah, and we are remodeling the ink. We can also imagine that there could possibly be some self-interactions between these particles, but we assume they are stable. And so in this case, there is just a single one-by-one matrix, and we are looking at eigenvalues of that matrix, which is a single number, and that number is negative. So in the middle, you can see it plotted in the complex plane. On the right-hand side, you can see it plotted as the sort of maximum real part of an eigenvalue, which in this case is again single number, as plotted for various values of k squared, various wave numbers, and if the wave number is 0, we really just have the matrix J. And so you can see this is negative, and what happens if we add something more negative to it? Well, it will just go and become more and more negative as we increase k squared. And so if we look at this, we start with something stable, but as we look at the various regimes of various wave numbers, we are still in the stable mode, and see the homogeneous steady state of the spatio-temporal system remains stable. And so with one variable, we can't see any patterns really. And so, well, maybe you can imagine we have a matrix with negative real parts as eigenvalues, and then we add something negative to it. We add two matrices which have eigenvalues with negative real parts, and we could maybe try to conjecture that that will always be the case, that we will just get altogether a matrix with negative real parts as eigenvalues, but that might not be the case if we go to more variables, or is it? And so let's try to test this. So let's look at the case with two variables. Well, we again have our matrix, and now it's 2 by 2 matrix, so it will have two eigenvalues. And we can notice that if we look at the trace, which is the sum of the eigenvalues, that must be negative, because trace of the matrix J is negative, because it's sum of eigenvalues with negative real parts. And then the diagonal matrix of di's, that's again has a negative sign in front of it. So the trace of the modified matrix JK squared is negative, which means that the sum of the eigenvalues of this modified matrix is negative. So we can conclude that at least one eigenvalue has negative real part. Otherwise, we would have this trace positive, right? And so that sort of restricts the various combinations of eigenvalues that we can have. Either both of these two eigenvalues have real negative parts and are real, or they have both negative real parts, but they are complex conjugate, or one is negative, negative real, and the other one is positive real. And the key question really is whether if we vary this k squared, whether we can go from the two cases with negative real eigenvalues to a case of positive real eigenvalue on the right. And so indeed, if we just for all values of k squared just have the two cases on the left, then again, we will have no instability. But if there is a value of k squared, a wave number k squared, where we go into this regime where there's a positive real eigenvalue, then the perturbation modes can grow, and we can see Turing instability and Turing patterns emerging. Well, how do we look through this space of various combinations of eigenvalues? Well, and a nice way to look at it is to try to draw this Poincare plane, where, well, if you look at how you can express the eigenvalues, you can realize that the characteristic equation written on the top in the middle can be expressed just in terms of trace and determinant. And so really all the eigenvalues can be expressed in terms of trace and determinant. And then based on the signs of trace and determinant, you can find various parameter regimes where each combination of eigenvalues will fall into. And so if we start at k square 0, look at just the eigenvalues of the matrix J, then we know that both must have negative real parts. So we are either in this case where they are both negative real, or they are complex conjugate with negative real parts. And then we can look at what happens as we vary k squared. And if you do the algebra, you can notice that the determinant is a quadratic function of k squared, and trace is a linear decreasing function of k squared. And so as a result, the red line in this Poincare plane will be a parabola. And if this parabola stays just in the regime where trace is negative, determinant is positive, then we stay in this regime where both eigenvalues have negative real parts, and then there's no instability. But possibly, if we have sufficiently nice parameters so that the so that in our case the determinant would go into some negative values as a parabola, then we can notice that we go into this regime where one eigenvalue becomes positive, and then we have this intermediate space of wave numbers in the plot on the right where patterns do form. And if we do the algebra, we can just look at the parabola, say at the determinant parabola, and ask whether it has a minimum which is negative, and that minimum that would occur in sort of positive values of k squared. And if that is the case, we can derive this condition which restricts the regime of diffusivities so that the patterns form. And if you actually also write down the conditions for the matrix J to be stable, you can try to get some intuitive understanding of what is going on in this case, because it's sufficiently nice and simple system with just two species, and you can realize that you are only in this case if the sort of diagonal entries and the off-diagonal entries have opposite signs, so you can start interpreting one chemical species as an activator of the dynamics, the other one as an inhibitor of the dynamics. And then you can notice that this condition for diffusivities means that the inhibitor must be much faster than the activator, so that you have long-range inhibition, short-range activation. And that's sort of the intuitive picture that we can get for these patterns to form. But as you can see, the patterns that form are, at least according to this linear stability analysis, always sort of stable in time, because there are no oscillatory modes, no complex conjugate eigenvalues with positive real parts, because that's sort of not possible, because the trace always increases. We are restricted only in the left part of the diagram, which we have here. And so that's sort of the big idea, and this condition is attributed to Alan Turing, who showed that quite surprisingly, compared to the case with one variable, suddenly patterns can form. And this was quite surprising, because people thought, as I sort of tried to suggest before, if you sum two matrices with eigenvalues that have negative real parts, maybe their sum will also have negative real parts, but this is not the case, and in this case it actually has quite striking consequences in pattern formation. And so the question that I ask and I want to talk about is, what happens if you go to 3 species? What happens if you have 3 variables? How can the patterns form there? And so that's the first story I want to talk about. And we'll start with a similar introduction. Again, you can notice that the trace is negative, and so the sum of the eigenvalues is a negative for any value of k squared. And so we are again in this regime where at least one eigenvalue must have negative real part. And as otherwise, if all had positive real part, this trace would be positive, and that's not allowed. So that leaves us with these 5 different combinations of eigenvalues. Either all of them have negative real parts, either complex conjugate in the first case, or or all of them are real in the second case, or we are in a regime where at least one of them is positive and real, or two of them are positive and real, or we have two that are positive but complex conjugate. That's sort of the options. And if we look at it, if we are just in the case where for any value of k-squared, we just stay in the stable regime, there is no instability forming and there are no patterns. But if we go into the regime where we have real eigenvalues with positive that are positive, then we can have these stable Turing-like patterns forming. And possibly, if we could somehow go into this regime where k-squared, as we vary k-squared and go into this regime where we have two complex conjugate eigenvalues that have positive real parts, and we can possibly have some sort of dynamic patterns that as these sort of perturbations grow, they also oscillate, and the resulting patterns could potentially be dynamic. And so how do we look now into the transitions? Now, if we want to use the analysis like before, we just had before trace and determinant, and it was relatively easy. We could just draw a plane and then somehow plot all of these different diagrams of the eigenvalues on the plane. But now we have 3 degrees of freedom, 3 variables, and it would be a bit more harder. We would need some sort of 3-dimensional space. And so for this reason, we'll sort of just look at this sort of graph of allowed and possible transitions, because if you look at the matrix that we are studying, as we vary k-squared, the eigenvalues will change continuously. And so there is just sort of only some of the transitions will generically be allowed. And so if we have very small values of k-squared, we are in the stable regime. But also if we have very, very large values of k-squared, then we have sort of a diagonally dominant matrix, and we also end up in this stable regime where all the eigenvalues have negative real parts. And so if this is the only transition that happens here just between this sort of 2 cases, then as k-squared varies, then we'll just have no patterns forming. But possibly there could be other things going on. Maybe if we go through the transition where one of the eigenvalues becomes positive, then we could have these Turing patterns forming. Or maybe if we have a transition where we now go into this regime where two of the eigenvalues are a complex conjugate pair with positive real part, then we can again form some patterns, but now in this case, patterns that are oscillating in time. And so how do we analyze this? And so the idea is still similar. We can go and try to express the characteristic equation, the eigenvalues, in terms of some invariant quantities like traces and determinants. And now we get one more thing. It will be the trace of the educate matrix, and again, trace will be linear, but determinant now will be cubic in k-squared, and the middle term trace of the educate matrix will be a quadratic. And there is something called there is another quantity that will be useful, and I'll also show you in a minute why. This is just a quantity where we multiply the trace and trace adjugate, so we get something cubic, and subtract the determinant, which is again cubic, so we get another cubic. And the reason why this is helpful is because there is a way to analyze stability in terms of these quantities of trace, of adjugate, trace, and determinant, and then this final quantity where we multiply the two and subtract determinant. And this is the Routh-Hurwitz criterion. And this says that if the trace of adjugate is positive, while all the other quantities that we have here are negative, then we are in the stable regime. And all our eigenvalues have negative real part. And so this should be true if k-squared is 0, which restricts sort of where our quadratic, linear, and cubic function starts, and also that is true, and we can check that if we go with k squared to infinity. And indeed, we have a sort of quadratic that that looks like this, sort of looks like uh, uh, a cup rather than a cap, and so on. And that's sort of determined by the leading terms of these quadratics and linears and cubics. And so indeed, if we go to very large k squared, we are again in this regime of stability. And so the interesting thing is what happens in between. So let's try and think a bit more about this transition that I talked about in the case of Turing-Hopf instability. Well, if this transition happens that I sort of now emphasize in red, then there is this case where the eigenvalues cross the line that determines the stability, the line with real part 0, and both of these eigenvalues are complex conjugate. And so we can go and try to analyze it when that happens, and so we just now substitute in the eigenvalues that are just a pure complex conjugate with no real part. And then we can go and take the real part and the imaginary part. And if we go and take the imaginary part and solve for omega, that gives us values of this omega. But we can notice that for this to be possible, the trace of the educate must be positive. And also, if we then substitute this omega into what we get from the real part, we get a condition that the sort of quantity that I used, that I denoted by dashed line in the previous figure, that must be 0. And so if we return to this figure, the condition to actually go through this instability is that this sort of quantity of traces multiplied minus determinant, that is 0. And when we have these zeros, the trace of adjugate is positive. And well, with this sort of criterion, it's just about sort of looking at maxima of cubics. And in this case, well, we can find a maximum of cubic. That's like solving a quadratic equation and then looking whether this maximum exists for a positive value of k squared and whether the value at this maximum is positive. Then we can also check and look whether the quadratic in this sort of regime is positive. And if we make these checks, that's sort of something you can do after some algebra. And I do not really want to go through all the details in the algebra. You can look at the paper, but you can, by doing this algebra, you can really go and get the condition in terms of just the diffusivities di and the elements of the matrix J that then tell you whether the diffusivities are in the appropriate parameter regimes for this Turing-Hopf bifurcation to occur. And you can really see you can just have a bunch of coefficients that you get in this sort of upper square, and that are just functions of these things, and then a bunch of inequalities, and you go and just check these inequalities. And so if you have your specific model for the chemistry, which now becomes hidden in these entries J, and you know the diffusivities, you can just go and check whether you satisfy these conditions, and if yes, you can have these dynamic patterns. Well, so what about now the previous Turing patterns? In this case, the eigenvalue is real when this goes through this transition, and so in particular at this transition, the eigenvalue must be 0, and so we can just put lambda equals 0 in this equation, and we get that the determinant is 0. But now, well, wait a bit, right? We have determinant that should be 0. Determinant is the multiplication of all eigenvalues, but there is this other possible transition that at which we also have determinant 0, and because the other eigenvalue goes through 0. And so the question is now, well, if we just look at determinant 0, which transition do we go through, and are we guaranteed that we go through this transition that sort of takes us from stable to unstable, and what is going on in there? Well, to look at this, we just go back to our diagram, and we know that this determinant is a cubic function that also starts already being negative at k² 0. And so we can conclude that there are at most two roots, two values of k², where we have 0. And we also know that we start and finish at the stable region as k² is varied. And so one case is that actually we just go back and forth and we pass through the transition twice, and that's fine, and we have the Turing patterns. There could be possibly the chance that you could try to hypothetically imagine that we go through both of these transitions, but that would mean that we would pass through the transition with determinant of JK of the modified Jacobian being 0 4 times. We go first one eigenvalue becomes real positive, then second eigenvalue becomes real positive, and then as we go to higher value of k², we go back, and again we get 2 more transitions altogether, 4 transitions, and so that's sort of not allowed because we have at most 2 roots that are positive. Or we could go into the stable region, and that's sort of the only final option, through the regime where the eigenvalues have are complex conjugate. But that's sort of where we said by definition that we call this sort of Turing-Hopf instability, and that's the instability we analyzed previously. If you go through this path, then you necessarily need to go through the other transition that we already studied. And we can go through it both ways, but whichever way you're going, you must be going through this transition. And so we can then conclude just by, again, looking at this the determinant now, and again looking at the maxima of a cubic and whether they are positive, and so by this sort of just graphical method, we can again find the conditions for Turing patterns to form, where we now see that this is exactly where Turing-Hopf patterns do not form. And then we are just in this case where we go back and forth between this sort of stable regime and then one eigenvalue positive real. That's when we have exactly 2 transitions through the determinant of 0. And we can find the conditions when this sort of happens. And so again, we have nice conditions in terms of just determinant, well, just in terms of Jacobian entries for the chemical reaction system in terms of diffusivities. And so altogether, we get this interesting picture. We can either have no patterns or stable spatial patterns or these nice dynamic patterns. And it looks very exciting because if we look and compare with the case of 2 species, we usually don't get these dynamic patterns. And if we look at 1 species, we get no patterns at all. And so we might be thinking as we go to more and more species, things will become more and more exciting. And well, for 4 species, you get to the case where you need to analyze, now look at quartic equations, and you would need to look at the maxima of quartic. That's like solving equation, solving for roots of cubic, and that becomes hard. And so we decided to take a different approach, and there's a work I've done with Philip Maini, and we decided to look at infinity and ask, when will a large complex system form Turing patterns? And so in the case of infinity, we again have our Jacobian matrix for the well-mixed system. But in this case, to approach such a complicated problem, we will look at ideas from random matrix theory. And we have imagined that this matrix have random entries. And so we look at the case that we can study easily analytically, so that we imagine that we have independent entries, and the entries on the diagonal have negative mean minus mu and positive variance sigma squared, and the off-diagonal entries have the same variance but mean 0. Why do we make this setup? Well, there is a nice result, done firstly by, who was it, Girko in this case of independent entries, I think, but the sort of best version so far we have from Terence Stahl, where they showed that irrespective of whatever distributions you are sampling from, as long as you are sampling from a distribution with these sort of means and variances, then your eigenvalues will always be distributed with probability 1 within this circle as you go to infinitely many variables. And this circle has center at minus mu, so that's sort of the expected value of the diagonal entries, and then the variance sigma times square root of n, where n is the number of variables that we are considering. And so by assumption, because we are assuming that we are starting with a system that when well mixed is stable, we imagine that this circle lies completely in this negative half plane in the complex plane. And so that sort of gives us conditions that these sort of intraspecific interactions must be stronger, sufficiently strong compared to the noise in all of these entries, so that we have stability. And then we look at this case where we look at spatial perturbations and we spatially perturb the system, and we look at what happens as k-squared increases. And in this case, there is again an analytical result where we can analyze where the eigenvalues are distributed. And in this case, where sort of putting something on the diagonal modifies the expected value of these diagonal entries, we just sort of modify the circular law. And indeed, if you have k-square equals 0, this just becomes the equation that you saw before. But as you go to bigger and bigger values of k squared, the shapes slightly change and the distribution of eigenvalue changes. But the key thing really is what happens with the eigenvalue of the maximal real part. And if you look at the simulations, in this case dots, where we sampled randomly a large matrix, you see that these maximal real parts decrease with increasing value of k-squared. This is not a coincidence. It's something that we can prove analytically. So if we look, I should have copied this function that you see on the right. That's sort of a function of k-squared and of the points in the complex plane. And this is a function that describes the sort of circle where the, or now modified region where the eigenvalues are. And this must have a sufficiently large value for lambda to be in this region. And so now let's imagine that this subset of the complex plane really goes into the positive real half plane. But if that would have been the case, then as k-squared increases, then f goes down. And because f goes down, then the value of f at this k-square is small than the value of f at 0. But for the value of at 0, we know we are in the negative real half plane, and then we use this criterion. We actually see that, well, if this was the case, then we go and get a contradiction, because the value of f lambda k-squared now is within the region, that is in the negative real half plane. And so really we sort of can prove analytically that that the eigenvalues just decrease as k-squared increases. And so that gives an interesting message here, because we might think that as diversity of patterns increases, we would just see more and more interesting patterns. But the thing is that the probability of observing these patterns goes to zero, because we are in this regime where the maximal real part of the eigenvalue just becomes more and more negative. And so we are again in this regime like with a single variable where things are just stable. And so we ask this question, well, maybe we could add something else than diffusion. Maybe there's some different transport mechanism for the molecules that could generate patterns much more robustly, even in large systems. And what would this be? What sort of interactions should we put in so that we generate patterns robustly? And so for that reason, we look at a general form of the transport, not just a diffusion. So we had diffusion in the model and added something more general. And then if you do the classical approach of looking at a stable steady state and then looking at small perturbations, going to Fourier modes, you just get this, where the first term is again the Jacobian as we had before for the well-mixed system. Then we have the diffusion term, but then we also have something like the advection term and a cross-diffusion term. And now, because we use these ideas from random matrix theory, we sample these matrices of advections and cross-diffusions with now expectations 0, but with some sort of variances that tell us something about the strength of advection and cross-diffusion. And in this case, again, if we started with k² equals 0, then we have just our modified Jacobian matrix being equal to the a Jacobian matrix of the well-mixed system, and we would have a circle that is in the negative real half plane. But now also because we sort of notice that diffusions cannot generate patterns on their own, we take all diffusions to be equal to each other. And in this case, just sort of look at the strength of advection and cross-diffusion. So that means that all our eigenvalues will be located within circles, because the expected values along the diagonal of this matrix will all be the same. And this is the equation for these circles. And we can look that if we have cross-diffusion and advection, we can actually go into these regimes of k², where we go past this boundary of real part 0, and our eigenvalues start having positive real parts. And indeed, just by looking at this equation, we can look at what is the eigenvalue with maximal real part, and then we can go and plot it. And we can even find the conditions where we are in which regime. And actually, if cross-diffusion is very strong, then we are in this regime where the eigenvalues become ever increasing with ever increasing weight numbers. That would sort of mean that ever decreasing very small weight lengths, which is like the inverse of a weight number, would be more and more unstable, which usually suggests that the system, that the original differential equation is ill-posed. So maybe, well, the models with strong cross-diffusion and many species are not very well posed. But if cross-diffusion is sufficiently small, and this condition in orange is not true, but advection is sufficiently strong, we always robustly generate patterns. So just by increasing the advection in the system, we can generate patterns robustly. And what about some sort of different interaction? So here we covered all sort of local interactions. So let's look at generalized non-local interactions. Again, let's look at the linearized theory in terms of Jacobian matrices. And in this case, we have this sort of strength of non-local interactions. Everything is captured by this matrix lambda. We assume that it has expected value 0, but variance s squared. And again, we can go and look at the random matrix theory and look at how the eigenvalues are distributed. And we can have an equation for that. And what we can notice that is that provided we make this strength of non-local interaction as n squared sufficiently large, we can always get this equality to be valid, or if you want to look at it, we can just solve for the eigenvalue maximal real part and then increase the value of Sn squared and add a fixed value of k positive, and then we can always make this sufficiently large so that this eigenvalue becomes positive, provided we have a function k that is positive. Well, which often is the case. The only way how you could get it is this sort of kernel of non-local interactions would be somehow very degenerate and would be zero, which is then like not having interactions at all. And so because we assume we have some non-local interactions, this value of k, big K, should be non-zero at least at some values of little k. And so we are able to just tune the non-local interaction parameters to make it sufficiently large so that the eigenvalue with maximal real part becomes positive, which sort of means that patterns can again form very robustly for non-local interactions. And so in summary, any form of repulsion or attraction, either being imposed by some sort of local forces of advection or cross diffusion or some non-local forces, can generate pattern very robustly. And so in summary, we sort of look at this case where we have patterns with one variable, two variables where spatial patterns can form, but they are not dynamic. Then we look at, and I showed you how you can get the conditions for dynamic patterns with three variables. And we can see that this sort of pattern diversity increases, and one could imagine that sort of patterns become more and more diverse as we go into a more and more species. But quite surprisingly, if you look at unstructured random system, the probability of observing these patterns goes to zero. And if you don't have diffusion, the opposite can be true. And then these patterns can form very robustly even if you go to a very large number of species, suggesting that maybe other mechanisms than mere diffusion can be used to generate patterns robustly in empirical scenarios. And so with that conclusion, I would like to thank you for your attention, and I welcome any questions.
Thank you very much. Thank you for the interesting talk, and probably I will